Today is Mario Day, and I want to give you a simple challenge. On screen, you're about to see 3 different games of Mario being played at the same time. One of them is being played by a human. You have a few seconds to guess which one it is. If you guessed option B, you'd be wrong. But you'd also be wrong if you picked option A or option C. Because, as you might have guessed, what you're actually watching is Super Mario being played by 3 different AI agents. And by the end of this video, you'll understand exactly how they learn to do that, from knowing literally nothing to pulling off techniques that even players struggle to execute. But to understand why this is impressive, we first need to talk about how humans play Mario. The original Super Mario Bros. Was released in 1985, and somehow, nearly 40 years later, its legacy is still very much alive. Modern games like Super Mario Odyssey prove that the formula never really lost its magic. At first glance, Mario seems simple. An Italian plumber jumping over enemies trying not to fall into pits. But it was just a matter of time for the game to be pushed way past its own limits. Nowadays, it has been discovered that it's even possible to inject your own code in the game. Just look at Mario World becoming Pong and Snake. At that point, Mario isn't even a platformer anymore, it's a programmable computer. And even without tasks, human players have reached absolutely absurd levels of skill. Just look at how insanely difficult triple share jumps are. So the question naturally becomes, can an AI learn to play Mario the same way humans do? Can it beat levels? Can it discover glitches? And can it ever reach world record level strategies? To find out, I decided to try 2 very different approaches, and the results genuinely surprised me. Method 1. NEAT. The first approach is inspired by Seth Blink's iconic 2015 video, which showed that AI could learn Mario through a technique called NeuroEvolution. If you've never seen that video, go watch it. It's what got a lot of people, including me, interested in this subject. I started experimenting on my own. I tried combining a genetic algorithm with a convolutional neural network and trained it for over 50 hours. It managed to reach the final staircase, but it never managed to go beyond that point. Eventually, frustrated, I decided to go all in on a specific method, NEAT. So, what is NEAT? NEAT stands for NeuroEvolution of Augmenting Topologies. Unlike traditional neural networks, where you decide the structure ahead of time, NEAT evolves both the weights and biases and the network's structure itself. That means the AI doesn't just learn how to play, it also modifies its own brain to actually learn the game. This has 2 major advantages. Firstly, you don't need to choose a network architecture, and secondly, the algorithm naturally tends towards the simple structure, and it still solves the problem. Now, here's how training actually works. At the beginning, the agent knows absolutely nothing. It doesn't know what Mario is, it doesn't know what Goombas are, so at first, it just stands still. Generation after generation, Mario does basically nothing, but just like Sisyphus, we force him to never give up. So, how does Mario actually learn? Well, we start with a population of neural networks that know absolutely nothing about the game. But every agent gets assigned a fitness score, based on how well it performs. It receives positive points for moving towards the flagpole, and negative points for dying. You can think of it as the carrot and the stick approach to training an animal. Use the carrot to reward positive behavior, and the stick to punish negative behavior. Except in this case, the animal is hundreds of evolving neural networks, and the positive behavior is running to the right without falling into a hole. After each generation, the fittest agents, the ones with the best scores, are more likely to reproduce, and thus create better AIs. Then the genes are combined and mutated. Most mutations make the agent worse, but every so often, one mutation makes it slightly better, and over time, those tiny improvements stack. You can actually see this process in the fitness graph. Long periods of stagnation followed by sudden breakthroughs, when the agent discovers something new, like learning when to jump. I also implemented elitism, a simple rule that says the single best agent never dies, so progress is never lost. Eventually, after many hours of training and without ever being told what Mario is, the agent learns how to play the game. Did you just see that? If Mario lands on the corner of a block with exact horizontal speed, he can jump again, but only on a single frame. This is a technique used by high-level speedrunners, and the AI discovered it on its own, all thanks to NeuroEvolution and hundreds of generations. Method 2. PPO. Some people might say that Super Mario Bros. Is too easy, or that the moveset is too limited. So for this second implementation, I wanted to train our AI agent to play Super Mario World. To do this, we'll create the environment from scratch by importing the game into Gym Retro. We'll have to locate the memory addresses that contain useful game information, for example, Mario's position, and we'll have to store those files in a custom JSON file. Once that's done, our Gym Retro environment is ready to go and training can begin. While Nietzsche showed us that AI can evolve to play Mario, there's a completely different approach that's become state-of-the-art in modern reinforcement learning. It's called PPO, or Proximal Policy Optimization, and it is one of the most widely used reinforcement learning algorithms. And unlike NEAT, which evolves entire populations of neural networks over generations, PPO trains a single agent in real time through continuous trial and error. When I say it's a state-of-the-art algorithm, I mean it. OpenAI 5, an agent trained with PPO, was the first agent to beat the world champions in an esports game. So, if it can master such a complex game, surely it can handle a plumber jumping on turtles, right? Well, PPO trains a single neural network by continuously adjusting its behavior based on immediate feedback. Think of it like this. The agent looks at the screen through a convolutional neural network, the same type of architecture used in self-driving cars and facial recognition systems. The CNN automatically learns to extract what matters from the image. For example, the position of platforms. Then the agent takes actions and is evaluated thanks to a reward function. Moving forward receives a small reward, reaching the goal receives a huge reward, and dying receives a negative reward. But here's where it gets interesting. To speed up training, I'm not just running one game of Mario. I'm running 4 parallel copies of the game simultaneously. And they all feed the experience back to the same neural network. This parallel training means that the agent learns 4 times faster than it would with a single environment. After training for several hours on 4 CPU cores, the PPO agent successfully learned to beat Yoshi's Island 1 in Super Mario World. But here's what's really interesting. The agent's playstyle is noticeably different from the NEAT agent. Even before the agent managed to beat the level it was being trained on, it already managed to beat the second level, while showcasing hard techniques that reminded me of arbitrary code injection in Super Mario World. Now there's a problem with training an agent on a single level. When you run PPO on just one stage, the agent doesn't actually learn Mario, it learns that level. Put it in a level it's never seen before, and it might not be able to beat it, even though in our case it managed. Maybe because the levels share many common textures. This is called overfitting, and it's one of the core challenges in reinforcement learning. The agent gets incredibly good at a very narrow task, and completely fails to generalize beyond it. In this case, there's an easy fix to this problem. To further increase the agent's performance, it can be trained on a set of levels. Before a new episode begins, a random level from the set is chosen, and so the agent must generalize its learning. But that was just the tip of the iceberg. Because while watching the agent beat all these levels was impressive, there was one stage sitting in the back of my mind the entire time. Donut Plains 3. A level that I considered impossible for AI agents. And so, can an agent trained with PPO beat it? And after thousands and thousands of attempts, here's the result. If you like this video, please consider liking and subscribing. If you have any suggestions or ideas for future projects, please leave a comment and let me know. If you're interested in seeing the code to this project, you can find everything in my GitHub profile, link in the description. See ya!